I want to ask you about an uncomfortable moment we've all tried to forget. You're 3 months into your project, you've prepped your samples, run the assays, you've spent late nights staring at spreadsheets. Your supervisor walks into the lab, leans over your desk and asks a deceptively simple question. So what are we testing here? Can you answer that in one sentence? And I don't mean what you're measuring. I don't mean what machines you're using, what protein you're targeting. And I don't mean what you hope to find. The question is, what are you testing? If your brain just scrambled for a second to piece together an answer, don't panic. You're in the right place. Let's fix that. Whether you're out in the field, stuck in the lab, or drowning in messy data, this channel is where you need to be. Because here we build research that actually works. I'm HARKing, and this is The Rigorous Researcher. Today we are looking at a fundamental, foundational concept that sounds almost too basic to discuss. What is your experiment actually trying to prove? Do you know that a huge percentage of researchers, including people with senior titles in research, rarely make this fully explicit in their work? And that hidden gap later creates problems that no statistical model can rescue. It creates problems that could have been avoided. Let's start with a massive point of confusion, that trips up almost everyone, especially in the early stage of their research career. There is a huge difference between a research question and a research hypothesis. The research question is your big, beautiful idea that's got you excited in the first place. For example, you have a question like, does high soil nitrogen availability affect wheat yield under extreme drought stress? That's a fantastic topic, right? But to be sincere, it's not an experiment. It doesn't tell you what you're manipulating. It doesn't tell you what you are holding constant. It doesn't tell you what you are varying. It doesn't tell you what specific claim you're actually trying to make. So your experiment needs a precise, testable claim. A real hypothesis is not the vague stuff you copied out of textbooks in undergrad or your school's repository of previous research. It has to be a razor-sharp statement about what exactly you're expecting to see, why you expect to see it, and under what exact conditions. So let's look at how we can change that question, that research question, into something that is testable, into an actual testable hypothesis. So the question is, does nitrogen affect wheat yield, during drought? But if you want to convert it to a real hypothesis, it's going to sound more like wheat plants supplied with high nitrogen will exhibit a significantly higher grain weight under a controlled 14-day drought cycle compared to a low nitrogen group, because nitrogen promotes deeper root architecture that maximizes residual soil moisture uptake. If you look at that statement, it's packed. We have a clear direction. There is an explicit mechanism, and there is also a direct comparison. And you have also provided a strict condition. If you look at that statement, you can design an experiment around that sentence. So more importantly, that sentence gives you the ability to be completely unambiguously wrong. Because in rigorous science, being wrong is not a failure. That's the entire point. If your hypothesis cannot crash and burn, you are not doing an experiment. You are not running a test. You are just running a demonstration. You already know what is going to happen. Writing out a null hypothesis can feel like formality, especially the way it's being taught. But psychologically, the null hypothesis is your most important guardrail. It defines the alternative reality you're trying to rule out. It described what I refer to as the boring world. And what do I mean by boring world? It's the world where your treatment does absolutely nothing. You know that's possible. Your variables don't even interact with each other. Every beautiful pattern you think you see is just random background noise. No effect whatsoever from your treatment. For example, in this instance that we're given, the boring world says the nitrogen doesn't change a thing. The grain weight will be statistically identical. The root system will not even grow an inch deeper with higher nitrogen. And in fact, if you see a tiny bump in your graph, it's just random. That is what the boring world is. So your null hypothesis will read something like this. Wheat plants supplied with high nitrogen matrix will exhibit no significant difference in grain weight under a controlled 14-day drought cycle compared to a low nitrogen control group. And root architecture parameter will show no relationship with residual soil moisture uptake. So your experiment's primary job is to give that boring world a completely fair chance to happen, to be true. If a hypothesis is written or your study is set up so that every possible outcome can somehow be twisted into a win, you're not practicing science. You are writing a story. You are writing a narrative. This is a junction in the road that many researchers walk past blindly, without realizing that they've made a choice. Even though they are blind about it, they've already made a choice. So we're going to be talking about directional versus non-directional hypothesis. So a non-directional hypothesis states that there will be a difference between your groups. That means something will change. But we are not calling the shot yet. We are not saying what direction is going to go yet. We just know that it's going to be different. Whereas a directional hypothesis makes a definitive claim. Maybe the metrics will go up, it will be faster, it will be slower in a particular direction. You know, in most of the researches we carry out in biological science, whether clinical science, agricultural research, we are not operating in a vacuum. We have mechanism from literature, from pilot data, from literature generally that we've already studied, and we know enough to make a directional call. And when we can, we should. Why? Because a directional hypothesis is much bolder, is a more useful claim. It provides, it proves that you understand the underlying mechanism of your system. But here is the trap. Never choose a directional hypothesis just because you think it will make your p-values look better. Mathematically, when you choose a directional hypothesis, you will run a one-tailed t-test instead of two-tailed t-test, and that automatically cuts your p-value in half for the direction you predicted. It can instantly make a frustrating, insignificant 0.08, for instance, turn into a publishable significant 0.04. But don't do it. So the direction has to be locked in by your theoretical logic before you gather your data. Looking at your results first and then retroactively tuning the direction of your hypothesis to match what you have already seen is a form of bias, and it ruins reproducibility of your research. It's called HARKing, hypothesizing after results are known. So what you need to do is to write down your prediction, you date it, lock it in your lab notebook, sign it, then build your design around it. Not change the direction of your hypothesis when you have already gotten your data already. Now, let's look at a concept from modern causal inference that is perhaps criminally undertaught in standard science recently, and that concept is the Estimand. Don't let the technical jargon scare you off. The Estimand is simply the precise real-world quantity you are trying to estimate. It's not the statistical test you're running, it's the actual thing in the physical world that you want to understand. So let's bring this back to the wheat and nitrogen experiment we're talking about. So you've set up your pot, you've applied the nitrogen treatment, and you're ready to measure, say, grain weight at the end of the drought cycle. So the question is, what exactly is your target Estimand? Is it the effect of nitrogen matrix on the specific variety of the wheat in that specific greenhouse or glass house during that specific month? Or is it the average effect across every major commercial wheat variety that is grown across the entire continent? Or is it the real-world effects under true farming conditions where soil types, wind speed, evaporation, and fertilizer application varies and is not perfectly uniform? Those three are completely different targets. An experimental layout that, finds the answer to number one might be completely useless for finding the answer to number three. So for instance, if option one is your target, you only need to buy one single sack of identical clone seed of maybe a single wheat variety. But if option two is your target, testing only one variety will be a massive design failure. You can't test just one variety. You have to source for seeds for the top maybe 5 to 10 most common commercial wheat variety that is grown across the continent. You plant them, you apply your nitrogen, you run the drought cycle, and you calculate your average effect across all of them. So if your target Estimand is poorly defined at the start of your experiment, your final numbers might be correct mathematically, but completely useless to the rest of the scientific community or the scientific world. So if a researcher finishes the experiment using only one variety of wheat, then they now write in their final paper that nitrogen improves commercial wheat yield across the continent. They would have committed a major methodological error, because they aimed for option two, but their design could only answer the question for option one. So by defining option two as your target at the very beginning, what you have done is you would ensure that your sample selection and experimental setup are actually built to answer that big picture that you claim that you want to make. So you need to know exactly what target you are aiming for before you start shooting. So how do we bring all this together into one actionable step that you can work on today? I want you to run what I call one paragraph test. Before you prepare another sample or buy another kit, force yourself to write a single paragraph that will contain 5 elements. 1, the core phenomenon you are trying to study. That is, what are you studying and why it matters? You will see that by looking at different literature. 2, your specific hypothesis, your directional prediction and the exact mechanism behind it. 3, your null hypothesis, what the data looks like if it doesn't work, if your idea fails. 4, your Estimand, the exact real-world metric you're trying to calculate. And lastly, the control group or the benchmark that makes your study a test, a genuine test, rather than a story, rather than a description. If you can write that paragraph cleanly, your experiment has a backbone, to be able to withstand brutal scrutiny, presentation, or peer review. If any of those 5 elements feel unclear, you need to step back and refocus your thinking. So lastly, I'm going to say, take time to define exactly what your experiment is trying to prove. It might sound like the most elementary step in the world, but in reality, it's the step where most mistakes happen. Give your project the time it deserves. Write your paragraph, test it against all those things that we have mentioned in this video. The mental heavy lifting you do today is going to protect your data tomorrow, will protect your experiment, protect your research, and we need to do the work. Next week, we are diving straight into the structural core of experimental architecture. So that we'll be talking about things like treatment, control, and comparison. And we're going to look at why your choice of control group is one of the most critical scientific decisions you will ever make, and how you can pick your control. Until then, think carefully, design deliberately, and trust what you build. See you next week. Bye.